So, first of all, thank you all for being here. I'll go ahead and get started. Today, I'm going to talk about all kinds of different techniques are just even ways to think through how do we build more resilient systems when we're throwing a lot of asynchronous processing, maybe distributed development in the mix. Queues, HP calls, whatever it's going to be. You're going to deal with this day in and day out because things go wrong all the time for us. Just a little bit about me. So I'm Jeremy Miller, coming from you from Austin, Texas. Completely over jet lag now, so hopefully I am coherent. Started my own company a couple years ago called Jasper FX Software. So you'll see a few of the products that I work on. I'm a long-term open source author in the .NET space. A few of you might remember Structure Map back in the day. Today we'll mostly be talking about two tools called Martin and Wolverine. This is meant to be about the concepts and the conceptual approaches, but I am going to be using my tools. And if I occasionally slide into a sales pitch, just let that go. All right, the main tool we're going to look at today is Wolverine. It's an open source framework. One of the many things it does is a messaging framework. A lot of the tooling we're going to show for resilience and exception handling, it'll all be using Wolverine. Don't worry if you're just kind of a quick show of hands. How many of you are using messaging, any kind of messaging framework today? A lot. So I think almost everything I'm going to show today is going to be present in other tools like in Service Bus or Mass Transit or Rebus. But the concepts are going to be the same, even if the implementation and syntax is a little bit different. We're going to also combine this with another tool called Martin, just because it's easy for me to work with. I don't know why that cut it off. So Martin is a library that turns Postgres into a document database and event store for .NET developers. Any place where you see Martin showing up in this talk, if you want to, just translate it to an EF Core DB context. All right. Just kind of setting the stage for the kinds of systems we're talking about. We're talking about any kind of system that may be doing asynchronous processing. Maybe you're doing it hopefully through queues, RabbitMQ, Azure Service Bus, AWS QS, Kafka. There's always more than I remember. Maybe you have some headless services that are running in the background, microservices. Today, people are trying to do those modular monoliths where they're still trying to queue even between modules within the monolith. And I think that's going to be plenty complicated, but that's not part of the talk today. We got databases in here. At some point, you're probably calling third-party web services from the outside world. Some stuff you control, some stuff you don't. Lots of stuff that can go wrong. So when we're planning these systems, and we're trying to make these things be resilient, look for a little bit of paranoia of all the possible things that could go wrong. Your database can get overloaded. This is probably the first thing that's going to happen under a load. You're going to start seeing problems. Connection pools will be exhausted. Maybe it'll time out trying to run a command. You could be seeing trenched areas with networks. Networks have all kinds of hiccups all the time. I had a really bad incident in my career very early on where we were seeing terrible network performance, and we found out later the IT guys in the central office were putting porn filters everywhere, and it wasn't configured right. Not that I'm bitter. It's unusual, but your message brokers, these are built to be just super reliable, but all the same, they can go down occasionally. Not often, but it happens. Your third-party systems, these are terrible, right? You have no control. You have no knowledge of what's going on. Ideally, you would like your web service and even the headless service, you'd like them to be able to work even if this third-party system's down. You can't do everything, but you'd like some work to still be proceeding. Okay? We're going to talk a little bit about temporal coupling. Our web service out in front, this is receiving requests from the outside world. This is your customers. You want your customers to have a good experience. You don't want your customers broken because the headless service is getting some kind of update or an index got corrupted or who knows what. For some reason, if this headless service is down, we want our web service still to be functional so our clients or customers don't even know anything's wrong, right? Okay. Just a few more thoughts about some of the things that can go wrong. On top of everything else, we're going to talk a little bit about concurrency, because that's a huge problem. That's a huge source of my consulting engagements and questions from my clients. Concurrency race conditions. We want to guard against those. We want to take some steps to, one, we don't have them, but two, we can recover from those. Other people are going to make errors in their code where there could be some kind of business rule that's just completely wrong, that's shoving everything in a dead letter queue. It's possible, not likely, but it's possible that we even made some coding mistakes, right? Right. So I would say the goal. The way I try to describe this is almost thinking of it as plumbing. You have work moving around the system in the form of messages. If you think about it as plumbing, we want there to be no possible way where messages could drop, where work just gets lost. In the end, what I think you want is you want a system that as much as possible can self-heal in the face of network problems, whatever it's going to be. As much as possible, we want to try to not require human intervention to get a system back up and flowing. So we'll talk a lot when we get into dead letter queue of when things shouldn't go to a dead letter queue. But the point is, as much as possible, the system should just work. And of course, try to keep the system up. All right, let's jump into just a little bit of code. We'll look at, it's all super contrived, unrealistic code, but let's look at where there's potential problems here. Say you have a single message handler, or this could be an HTTP endpoint coming in. Hang on, folks. There, that looks like code now. So this could be a message handler in a headless service, or if it's an HTTP request, kind of pretend it's coming in. We're doing a lot of things here. Where, first off, so I think this is somewhat based. The U.S. introduced a new beginning of maybe quasi-national health service about 10 years ago. If you follow U.S. news, the Obamacare thing. Part of it, and I was peripherally involved with this, there was an external web service. It was actually built by a Canadian company, so we're going to blame Canada. That was responsible for taking user information and verifying that they really were who they said they were. So at some point, if you're making a request to, I want to get health insurance, the big system had to call out to this one web service to get this identity verified, say who they were. Didn't work at all when it first came live. My friend that was working with this said, "Hey, Jeremy, this is going to be a disaster. We haven't even been able to test against it live, and we're supposed to be in production next week." But anyway, the point is, this is a great example of we got to call out to a third-party system. Here, I'm trying to do it in line. So there's all kinds of problems, potential problems. One, we could have a problem just right then and there, just doing a simple lookup of, hey, you're referring to an existing profile. I'm going to go try to see if we've got it saved. I mean, you could technically get a database error of all the normal sorts here. When we start to try to call into the database or call into this third-party system, there's a world of problems this could be. But moreover, we're making our system just wait. Do a bunch of work and then go wait for a response from somebody else, and then in line try to go do a bunch more work. So we get into this a little more. There's all kinds of potential problems, and here we've even got more. We got some business logic going on. We're going to try to save things to the database. We're going to send another message out to say, hey, this coverage was requested. We've captured it. Now, can you go work on it? Now, you notice we're sending the message out before we save the changes. So we'll get into this in a second. That's a potential race condition. Okay. So let's first start with the idea of a transactional outbox. Just quick hand, how many of you are knowingly working with a transactional outbox of some sort today? Quite a few hands. Um, let's talk about that and remember why that's important. We're going to come back to a simpler example. All right. So, really simple. Inevitably, we're going to create a to-do system. And when we do our to-do system, this up top, this Wolverine HP handler, not much going on here, but getting a request to create a new to-do, we're going to record it in a database, and then we're going to send an outgoing message that's assigned to do. We're going to capture it real quick, and then we're going to drop it in a local queue off to another handler that is going to figure out who to assign it to. Let's pretend this is really complicated logic for the assign. Right off the bat, let's talk about this. So we are trying to send a message, and we're trying to save data. The message refers to data that's just been saved. At this point, so we have a potential race condition. If the message happens to get out through a queue and get off to the handler before the to-do is actually saved, it's going to blow up. We don't have any way of recovering. Another sense, if it's also possible that the transaction fails, the message gets out, and it's a ghost. There's also the possibility that the transaction fails. Well, you get the point. We need both things to succeed, both the outgoing message and the final storage. Okay, so this is where a transactional outbox comes into play. Now, just a little more, things that show a few more things that are going on. This is looking at the service bootstrapping, and let me show you where I've added a few things. Adding Martin to the picture. We're going to do a demo in just a second. I'm just telling it, integrate with Wolverine. This is just going to add transactional outbox mechanics. Mechanics will be different in every tool set. You just see a little bit more what I've got highlighted up there. For every queue, I want every queue to be durable. That means we're just going to apply the durable inbox, outbox stuff to it. Let's go right to a coding sample. So our to-do handler, if this works correctly, we're going all the way through. I want to look at a test real quick. We'll run in just a second. So just throw more tools at you. There's another related tool called Alba. I'm just using as a test helper. This is strictly a wrapper around Web Application Factory. But we're going to bootstrap our application just the way it was. And we're going to run an HTTP request through to create a new task to book a train ticket. So our to-do endpoint should receive that description. It should create a new to-do entity, and it also should kick out an assigned to-do message, which we expect to be handled in a local queue. That handler, it's not doing much more than saying, hey, let's just tell Jeremy to do it, and we'll go ahead and save it. So far, so good? All right, so let's try to run this whole thing. Okay, I just happen to like Postgres, tends to work really well with Docker, so we're just going to spin up a quick little Docker container for the Postgres database after I make sure the Docker is actually running. Because it's not a talk if something doesn't go a little bit wrong. Okay, we got a little Docker database. And our test, we're going to spin up the application. We're going to run a request through. I'm using a little bit of Wolverine test helpers just so that it can watch and track that any asynchronous behavior that started completes before we go on with our test. Just a way to be reliable. From the request, I'm going to read out the response. and because that's going to give us what the task ID of the newly created to-do was. And then we're just going to check in the database and see that it was created the way we expected, and also the secondary response happened as well. Do this real quick. No. 1 second. This is why you do not do code samples right before your talk. Okay, so we're green. I know it's super tiny because I don't actually know how to make that bigger. So our test worked. We spun up the database. Let's look at some of the pieces just to kind of prove what's going on here a little bit. So on the fly, oh, come on, make that bigger. So in this case, it's a local queue. Wolverine's actually creating some new tables in our Postgres database, and that's all you're seeing here. This is the message that went through our durable queue. So at the time that we are running this this to-do endpoint, when we're returning a message and also trying to store data, the whole combination here, it's actually persisting the whole outgoing message body in the database itself. In the same transaction, in this case, the same network round trip. Both of these things are going to happen at the same time. After the transaction succeeds, it's going to release the outgoing messages. The outgoing messages will actually go into queues, whether it's RabbitMQ, Azure Service Bus, or whatever it is. The important point here is we're going to make these things succeed or fail together, and the outbox is going to control the timing. The database transaction always has to succeed first before any messages actually go out. That solves a race condition. That race condition, that's something I have absolutely seen people doing web services. Maybe you weren't aware of this. We had something in a former employer where the database was really slow for some reason, but our queues could be lightning fast. And we were seeing in production issues with this kind of race condition where the message was getting downstream before the database persistence had been done. We fixed this by rigging up, once we understood what was going on, we rigged up our own kind of homegrown outbox for our web endpoints that solved the race condition. In our case, though, when we're talking about resiliency, some of the other values of doing this, if our web service is capturing this work and just happens to die before the follow-up assign works, when the application is started up, if you've done your homework right with your transactional outbox, you should be able to recover these tests and just keep on going. Okay? That's the biggest thing. We have created a durable system. Even without external queuing here, this system is able to recover from crashes, restart, recover work. Work does not get lost in this case. I'm sure it's still possible somehow, but as far as I know, it's resilient. All right. So that's a little bit of error handling, but now I just want to go back to, let's go back to put our design hats on a little bit. And how big should a message handler should be? How many responsibilities should have? You're probably thinking single responsibility principle should probably be finer grain, and that's kind of where I'm going here. So kind of asking yourself, heuristics, maybe some questions to ask yourself to reevaluate any handlers you're either writing or working with. What steps within this logical process have to succeed together? You know, like we all know the famous case of if you're moving money between two accounts, the credit and debit needs to happen together, right? A lot of times you can get away with something being more eventual, but just kind of ask yourself what has to succeed or fail together, or what could be done independently. And then also thinking what will be likely to fail independently. Coming back to our too busy handler here. It's scar tissue, but I want to urge you to have some extreme paranoia about any kind of external dependency. Right here in this example, I was doing the call out to the external website, web service inline here. Got a pretty good idea that this is likely to fail at different times than our code that's just doing databasey stuff in our own world and business logic. Ideally, I think as a default, I usually urge people I work with, my clients, almost automatically wrap any call to an external system like this in its own retry loop. This should be its own handler, such that maybe you're verifying it up front, you're sending a request to call this third-party service, so it can be in its own queue, own little isolated handler. It can have its own retry, and we'll look at it in a following section. We're going to throw circuit breakers on it, so we can stop that. But we can let all of our work that can go on in other queues, so we can be catching up, let that work flow out. Don't, as much as possible, try to isolate the rest of our system from this piece here. Some other thoughts as well. So a framework like Wolverine or Mass Transit or In-Service Bus, any of those things, they're putting automatic performance tracking around your message handlers, most likely. Wolverine will export open telemetry traces, just all the good stuff you normally want. So you get that kind of performance tracking for free with your framework. So, again, taking this example, by moving this to its own handler for free, we get performance tracking against more or less isolated against this work here. And that's something that can provide some value for you as well. You can certainly do that with explicit code, but my take on that is to try to keep your code as low ceremony as possible, not force your developers to have to do a lot of explicit logging code. Your mileage may vary. Here's another one. Think about what can be parallelized and what can definitely not be parallelized. By having smaller work go through separate queues, you can control the potential parallelization directly at the queue level. Like, let me step into something real quick. Okay. So in a later section, this identity verification, if we know it's going to be really bad. About 5 years ago, working with a client that needed to interface with a third-party banking web service and written in enterprise Java, be afraid already, right? And it actually had, the web service API had a limitation that it could only handle one request at a time. Yeah, and this is like 2018 when we're, all modern and stuff, right? So the way we had to deal with it is to run the work that's going to talk to this web service. You had to run a single file sequentially through a single queue. We could potentially do the same thing here. This is some work where I was introducing RabbitMQ into the mix, just to have an external queue. I want to publish only that message there. Here's where I'm over one. This is something to be aware of. By isolating this message here in this one queue, we can set this to be strictly sequential, which unfortunately means only one listener running on one box. It's strict sequential, but that also means you're going to run slower. The other work, maybe some of the other work can run in parallel. Let that work happen in parallel. Let it go faster. You may have to create a bottleneck here, but we can isolate that bottleneck to just here. Third-party system services suck. All right. In your own work, kind of forget about frameworks for a little bit. There's a popular library called Poly. It's actually embraced by Microsoft themselves. You'll even find it integrated directly into HP Client, a lot of other places. But if you need to kind of create your own resiliency and retry policies for kind of one-off behavior, this is really, It's the only library I know of in town that does this kind of thing. So just thinking about errors that are truly transient. Network hiccups, database timeouts, your connection pool is exhausted. We use this directly inside of Martin itself, buried completely inside. So come back to your code. So like this simple place here where all we're going to do is try to load an entity out of the database. There's always a possibility that there's database hiccups right in there, especially when you're under load. Same thing again when it's doing save changes. Deep inside the Martin internals, this code here, this is where like the save changes. Let's find it with the badge. It's actually here. Deep inside, let's make this prettier. Inside of this execute async, this is running inside of poly. So we're going to do our actual work of just executing a database command. Wrapping around poly here, let me show you our defaults. We're looking for the kind of exceptions we know are typical transient exceptions. That these are things where you can probably get away with retrying. And this is an allow list. Don't do it willy-nilly on every possible exception type. But these things we know are exceptions that can probably be recovered from. System, I should say in Martin, we are intercepting a lot of these raw exceptions and trying to give you a more realistic exception when we can. So things that are like an optimistic concurrency exception. Things that are real logical exceptions, or you tried to update a document that doesn't exist, they'll get a more specific exception so they don't get caught on this, right? Because you don't want to keep retrying something that can never work because that'll blow your system up. And I guess how I know that. But this is our default setup. What we're going to do is we're just going to do a retry, and we're going to do something, the exponential back off. And all that really means is you're going to retry once after, say, 50 milliseconds. And if that doesn't work, you're going to wait even a little bit longer. And after that, longer still. What you're trying to do here is you're kind of creating an error handling policy of, I think my system is just stressed, overtaxed, right? So by doing retries completely in line, what we're de facto doing is slowing down our system, kind of giving our system a chance to just kind of slow down, wait, go at a slower pace, and hope that whether it's your database or whatever it's going to be has a chance to recover and then proceed more normally. The queuing in our distributed systems, that helps a lot too. That helps control the load of your database. You kind of moderate things that you're going at more of a steady pace rather than at the full speed of incoming requests from the outside world. It's another thing to think about. So that is poly. That's great for like little intermediate steps where we've built the command, we know exactly what we need to do. It didn't work because of network hiccup, just retry it immediately. In other cases, your whole command may fail. Who knows why, but it's probably advantageous to start the whole command over. Maybe you had to look up initial state. You start from something else that might have changed, but you need to start over on the entire command from the outside. And that's where Wolverine or a mass transit or a service bus is going to come into play. So just thinking about some of the exceptions and some of the things we can do. You know, we talked about transient errors. Transient errors that may tell us, hey, you know what, the system is just overtaxed. It's too busy. Let's slow it down. We're going to put some retries with delays in line so it doesn't try to take on more work. It's just going to pause, stop, let external resources try to cool down. That's what I'm doing up there with this faked up network timed out exception. Trying to get smarter, just tell it, slow down. If you match on this exception, just hold on. Other cases, line 22 here. Maybe you are trying to do some kind of pessimistic locking. Hit this with a banking application a few years ago, where you could detect that, hey, somebody has a pessimistic lock on this bank account. So there's probably nothing wrong with what we're trying to do. It's just we're not allowed to proceed right now. What I might do instead is I want to let other work go through. So I'm going to take this current message and I'm just going to go stick it right at the back of the queue and let it flow through with the hope that the lock is cleared out by then. Or instead, if I don't trust that the pessimistic lock it can be done that fast, with Wolverine I can say, I want to take it completely out of the queue and I'm going to go put it in a scheduled timer. I'm going to say, I want you to retry a handful of times, like wait 5 minutes, or and the next time try 10 minutes, or in the particular case I'm talking about, it was so bad we probably would have done a whole hour. Right? We're trying not to lose any work. We're trying to let it flow. We're trying not to let it go right to the dead letter queue. I should say, any place where I'm not explicitly saying move to the dead letter queue, Wolverine's moving it to the dead letter queue after you've exhausted all your other tries. But, again, we talked about don't make your system retry things that can never work because that's just going to blow your resources. So if we get an exception, validation exception, we know this message is bad. Maybe you're trying to assign a to-do that doesn't exist, whatever it's supposed to be. You should be handling that inside your own code gracefully and never throwing an exception, but, it happens. But any kind of exception that tells us, hey, this message is never going to go through. It's not valid. Something's wrong with it. I'm just going to immediately move it to the error queue. Don't retry. Don't pass go. Don't collect $200. Just toss this thing away. Or if you want to be more draconian and you don't want to clutter up your error queue with something you don't care about, or like a message just no longer matters, you could choose to discard it instead, and Wolverine's just going to throw it away. Any questions about any thoughts about anything before I move on? Yes, sir. So these are all fall through and matchers, and it'll be evaluated in the order that you're doing this. So if there's any problem with precedence, or if you're getting pickier, and it'd be the same thing with poly. Like if you need to do some more specific stuff about, well, if the validation exception message says this, you just move it up and down how it's defined for precedence. Does that make sense? Okay. And that's actually a good question because that will trip people up. It is order of precedence here, so just be careful of the ordering.
How about when if the data is only valid or should be processed in a certain time, otherwise you don't have to process it anymore. It's just
Yeah, in that case, you really should be handling it within your handler. Ideally, because exceptions are expensive, but that's where this discard thing would come in here. So you might get a little bit smarter, and again, not to sell Wolverine too much, but you could be finer grained with your what to do. You could put custom logic in that we could be smarter about discard this one, or send a message off to this person. Hey, Frank, you messed up. That kind of thing. Yes, sir. Oh, right. So every .NET developer worth his salt has a collection of silly little extension method helpers in a shared library somewhere, and none of those libraries overlap, so we all have our own. It's the equivalent of saying timespan dot from minutes. Here, it's in a helper library behind all this stuff. I mean, everybody's got something like that, and we all call them different things. They overlap. It's like my grandmother used to have a junk drawer of random screws and hinges and stuff like that. That's your extension library. Okay. Dead letter queues. I'm going to refer you to the old Enterprise Integration Patterns book. It's like a 25-year-old book. It is probably held up better than any other design patternsy kind of book. If you're doing any kind of distributed development, this is still very worthwhile. That's their um, that's their graphic from it. Again, this is the early 2000s, so that was probably impressive at the time. Um, I don't have a great demo for this right now, but your dead letter queue, some tooling like Azure Service Bus has a really good built-in model. So messages that are undeliverable or that are unprocessable, slap it into some kind of dead letter queue where hopefully you have some kind of UI where your support people can look at these things and see, no, I can throw this away, or maybe even change the message and try to manually reply it after something else is fixed. This is like so using this metaphor of don't let your pipes leak, the dead letter queue, it's the equivalent of going to an extremely old building with a leaky roof and putting a bucket down to catch the water that drips out. That's your dead letter queue. You got to have it just in case, but you try not to let stuff go there. Now, back to our third-party systems, because things just stink. Or maybe it's your own system, who knows what it is. Circuit breakers. What if, in terms of processing calls over here, we determined that this thing is down? It's either down or it's so unhealthy, we need to stop it. Okay, so this is where a circuit breaker pattern comes into play. So for this third-party system, I started to put a little bit of a rule of we're going to listen for that message. We're going to publish that message. We're going to run it through a RabbitMQ queue just to let it kind of back up as we need it. We played around with ordering. Now I'm going to apply a circuit breaker on it. And what this is doing is, it's all lots of defaults. Let's see. In a certain pattern, a certain time period, if we see that calls into this third-party system, if it's failing 10% of the time over a certain amount of time, we can make a judgment of, hey, this is unhealthy. I want to slam it shut. I'm going to close the circuit. I'm going to pause it for 5 minutes. Let this thing recover. I'll retry it then. But stop the listening altogether. Don't run messages through. Don't let them continuously fail and just wind up in the dead letter queue. Couple things here. You don't want to lose work. You don't really want a ton of things to go in the dead letter queue. It's a lesson I learned a really hard way in the past. You don't want to keep working this distress service by sending it tons of more requests. So just stop. 5-minute pause. You can configure this. Just stop. So I kind of as almost a default recommendation, anytime you're calling into some other service, another team, or even, maybe even any internal web service that's problematic in the slightest, throw some kind of circuit breaker on here just so work can stay in the queues instead of drop into your dead letter queues. And also, always, to keep saying that over and over again, give the distress service a chance to recover. I'm also going to exclude there's certain exceptions. Again, we should be dealing with all logical errors in your own code, not throwing exceptions, but it still happens. We can tell the circuit breaker, hey, these kinds of exceptions, these don't count. If it's a validation error, instead, I just want to discard it. Don't count that towards the circuit breaker failures. That's getting a little more fine-grained in your approach, and you're going to learn as your system goes on what kind of exceptions are being thrown. You'll kind of tune this over time. But more draconian. I know a lot of people deal with these kind of rate limiting problems with third-party systems, or I ran into a case where our web service dependency could be misconfigured. You could tell from an error code that it was just down. It was never going to work. Maybe you can actually detect hey, no matter what, this one exception means I got to stop again. It's the same kind of thing. Like say if we hit the rate limit exceeded exception, we know nothing's going to go through for a little while, so just pause the listener again. This time, no sampling, no fancy stuff. Just pause it right now. But I'm also going to take this current user, this current message, and I'm going to go throw it right back in the queue because I know it could probably succeed later, but I'm going to go slap it back to the end so I can deal with it later. So that's another way of just dealing with these external services where it might be down. Try not to lose data, stop, slow down, but try to restart later, hopefully. Yes, sir. Um, so, the question, do you just want to kill the instance? Um, it's beyond the scope of my talk. You could do that as well. I think you would probably need to dip into some kind of custom handler that triggers a shut this kind of thing down. It's not something I have a sample for. Now, are you thinking too about things like some kind of cloud service, the Kubernetes thing? Yeah, you can do that as well. That's just nothing I've tried to do myself. But I think that's a really good point. Talked a little bit about concurrency of just you got a whole bunch of people out there using your UI and maybe they're clicking things too fast. Maybe two different people are trying to edit a to-do or a task item or something like that. How do you recover from that? How can you protect your system from that? Let me look at the first couple things. Let's look at the first two here. There we go. All right. So let's now build a task tracking system. Okay. And apologize for this a little bit. By chance, have any of you used event sourcing in a system before, or at least learned about it? Okay. Not a ton of hands. It was just an easy example to show. We're going to use event sourcing in this particular task tracking. Just thinking we got a very handful of events. A task is created, it's completed. Individual items within it may be added, completed, removed. So the raw system state is tracked as these little events that are emitted for a logical task. Okay, so far so good. Another little helpful item. So I'm going to call the whole thing task item. In case you don't know this, it's really, really painful if you have a custom type in your system called task. Your IDE will yell at you forever if you do that. You'll get so confused. So track task, just a little bit of work here just to kind of, this is how I gather up these events and I know what my state is. Up top, we have a single handler where, very contrived, where if we catch the completion of a certain task item, I also want to look at the current state and see, is this the last task remaining, the last item remaining? And if so, I'm going to yield up another, hey, the task is done. We're done. That's it. Last one. This is extremely vulnerable to concurrency issues. If we have concurrent requests coming in for finishing item 3, 4, 5 all at the same time, they're all dealing with possibly obsolete versions of the track task. And this calculation at runtime of, is this the last one? They may not be getting the right data if they just magically be happening at the same time. All right. So what we need to do is have some way to either detect that and retry or to stop it, whatever it's going to be. We got a lot of options. Uh, the simplest one here, and I just apologize because there's a lot of magic behind it. This is already opting into a little bit of optimistic concurrency automatically. At the time that this transaction is committed with whatever these items are, if we're recording as this starts, the Wolverine Martin combo is recording. This is the current version of the track task. Maybe it's a version 3. When it tries to commit, it's going to say, I want to update this if it's still version 3. If it's not, if somebody else has gotten in there in the meantime, it's going to throw a concurrency exception. If we get a concurrency exception, it may be perfectly valid to just, hey, you know what? We just need to retry the whole thing. Stop, pause a little bit, and then we're going to retry the whole command. Because this particular command, we're trying to process logic on the existing state of the tracks task. Let's start over. Let's get the latest version of this track task and just proceed normally. That's optimistic concurrency. We're going to pretend that we can go ahead and do this, but we're going to let it fail at the save changes moment. We can do this a little bit faster. It gets in a little more complicated stuff. Now, you'll need to cooperate a little bit with your UI people probably, but if the client that's issuing these commands can tell us, I'm issuing this command to you, I think the existing version of this track task is version 5. And again, that's a little bit of magic, but this combination here, the full critter stack, that's actually enough that even at the time, even before we call this, we can check it right there and we can admit the optimistic concurrency failure faster. So that's even a little bit faster to just retry. The optimistic way is always going to be faster. It's just you're depending on it to throw an exception. You have to have that concurrency exception handling. Instead, it's always more expensive. You could opt into some kind of exclusive locking where I'm gonna stop and wait for a database lock before I let this go on. That's always a desperation move. It's there, you have to have it, just know it's in your back pocket. Try not to do this because it can get you in a deadlock situation. It's gonna work the database longer, harder, but you always have this option, or serializable database transactions. Or you got a couple more tricks. You can try to use multiple. We can do this trick where you say each queue is single file, but you can use more queues. So say if you're in a multi-tenanted system, you may say every request for tenant A goes in the tenant A queue, tenant B in a tenant B queue. Maybe they're single file, so that'll prevent concurrency errors within logical tasks for that tenant, while still having some parallelization between the tenants themselves. That's one trick that's been successful for some of my clients. You can always work. There are some tricks. Just I know this is a very Microsoft .NET centric conference. Azure Service Bus, you could use you could publish with message groups, and that would force Azure Service Bus to order messages one at a time for a particular task for you. That, again, it's a heavier weight thing. It's a little more complicated. It's going to slow down your system a little bit, but you can make Azure Service Bus be a message sequencer for you, and that's super duper handy. Before we get out of here, be paranoid in your own code. I've focused so hard on exception handling for the most part. A little bit on message handler, but in your own code, just be paranoid about the validation. You don't really want to be throwing validation exceptions. You want to be handling this cleaner. You really just don't want to trust anything about the current state coming in. It's not paranoia if they're really out to get you. Okay, and then finally, because I'm running out of time, just some other topics that I could not get to today. Just you may want to evaluate as well. There's an idea called back pressure. It's actually supported by Wolverine itself in some places, where if you can tell if you're sending a lot of messages, sending work off to somewhere else, and you can detect that somewhere else is busy, you may slow down, purposely slow down, and just stop taking work. With Wolverine, if it will limit how many messages it's pulling off the queue at a time, if it's too busy, if it builds up, that's just protecting yourself from memory pressure. That's advanced stuff. There's certain kind of messages where it may be super advantageous to do some message batching. This is all about round trips to the database. Maybe you just kind of let it pull up and handle in big batches. With the downside is that makes it harder to figure out where you might have poison pill messages and what's bad, but that's a way to be a lot more efficient. And some of those other things. Absolutely, if you're going to do anything remotely in this world, invest in open telemetry tracing. I think at this point, this has come so far so fast in the last few years that every tool like this is going to support open telemetry tracing and metrics. You absolutely want to make sure that's turned on in your application if you can. That's going to be your best possible way to understand how messages are flowing between items, what's succeeding, what's failing, and all that. And then lastly, the build versus buy. I'm very much on the side. I'm biased, but I'm very much on the side of this stuff is very complicated. The Wolverine stuff I've shown you, it's the new kid on the block, and it's still almost 10 years old. The fine-grained quality aspects of resiliency are very hard to build. You can do very simple message handling with bespoke code, but the really hardcore quality and resiliency, I think it's going to be a lot easier to pull something off the shelf than try to build that all yourself. But that's just an opinion. And on that one, folks, thank you. You've been a great audience, and I'm around a couple hours. Thank you.